Welcome to The Explainer. So, if you've ever stared at abstract mathematics and thought, wow, this looks like a wall of totally impenetrable code, well, you are in exactly the right place. Today, we're going to be decoding raw set theory. Specifically, we're looking at how math creates actual rules for sorting elements. We're going to break the whole thing down step by step. It's going to be efficient, super focused, and honestly, it's a lot of fun to unravel.
Okay, let's dive into this. How do we create order in math when things aren't perfectly sequential? I mean, in everyday life, we're completely used to things lining up in a perfect straight line, right? Like a ranking from 1 to 10, or a simple timeline, first, second, third. But mathematical universes are incredibly vast and deeply complex. Not everything fits neatly into a single file line. Some things are related, some aren't, and some stand side by side in a hierarchy. So how does mathematics handle this beautifully messy reality? How does it structure the seemingly unstructured?
Section 1. The Laws of Ordering. Decoding the partial order relation. Think of a partial order as a strict rulebook for a brand new mathematical universe. Before we can organize the chaos, our relation has to satisfy 3 unyielding pillars. First, it must be reflexive. That just means every element relates to itself. Second, antisymmetric. Basically, if A is related to B and B is related to A, well, they must be the exact same thing. No two-way streets here. And third, transitive. If A relates to B and B relates to C, then A absolutely must strictly relate to C. If even one of these pillars fails, the entire structure collapses, and we do not have a partial order relation. Section 2. The arena. Enter the Poset. Now, what's really interesting about this slide is how we shift our focus from those abstract rules into the actual mathematical arena they govern. So what exactly is a poset? Well, it's short for partially ordered set. Simply put, it is just a normal, everyday set of mathematical elements that has adopted those 3 strict laws we just covered. The moment a regular set agrees to play by the reflexive, antisymmetric, and transitive rules, it evolves. It transforms into a poset. It's a really fantastic example of how applying a few rigorous boundaries creates an entirely new structured entity in mathematics. Section 3. The inhabitants. Real-world math examples. We are going to prove these posets actually exist by looking at the inhabitants of completely different mathematical neighborhoods. Take a look at these 2 distinct examples. On the left side, we have the subset relation. That's all about containment, which smaller groups fit entirely inside larger ones. On the right, we have integer divisibility, which is about pure arithmetic, specifically which whole numbers divide cleanly into others. Now, visually and conceptually, they look completely unrelated. Yet, because a number always divides itself and a set always contains itself, both of these perfectly follow our 3 strict laws. They're entirely different mathematical neighborhoods, but they're governed by the exact same abstract code. Section 4. The map. Visualizing with Hasse diagrams. Let's move to and see how this builds from our concrete examples into the ultimate map we use to visualize them. If a Poset is a landscape of elements connected by hidden rules, we desperately need a map to navigate it without getting completely lost. Enter the Hasse diagram. It's a graphical representation of a Poset. It takes all those invisible, abstract relationships, the power sets, the dividing integers, and it plots them out into a clean visual hierarchy. You are basically looking directly at the architectural blueprint of a partially ordered set. And this brilliantly illustrates the concept of addition by subtraction. Notice how it intentionally omits reflexive loops, which are elements pointing back to themselves, and transitive edges, which are those leapfrog connections, jumping from the bottom straight to the top. Because our 3 laws already guarantee those connections exist, drawing every single one of them would just create an unreadable, tangled mess of lines. So by stripping away the obvious connections, the Hasse diagram achieves incredible, elegant visual clarity. It literally leaves you with only the essential framework. So where else in mathematics, or even in your own life, might these hidden partial orders exist, just waiting to be mapped? We've journeyed all the way from strict, abstract rules to incredibly clean visual diagrams. We've seen how messy, non-sequential data can be beautifully organized simply by applying the right laws. I really want to leave you with that provocative thought. Once you understand the rules of the Posets, you start to realize that structure is everywhere, hiding right in plain sight. Thanks for watching.